About 66 million years ago, a massive, 10-kilometer-wide object from space struck Earth, triggering the fifth mass extinction event in the planet's history. This catastrophic impact caused wildfires that raged across continents, set off enormous tsunamis, and ultimately wiped out nearly 75% of all life on Earth. The impact was particularly devastating for non-avian dinosaurs, marking their extinction. The collision left behind a vast, 80-kilometer-wide crater, now known as the Chicxulub crater, located beneath the Yucatan Peninsula in modern-day Mexico. For many years, scientists believed that a single, massive chunk of rock was responsible for this extinction event. However, in a groundbreaking discovery, researchers have found evidence suggesting that the Chicxulub impactor was not alone. Instead, it had a companion whose impact resulted in the newly discovered Nadir, NAD, crater. So how did scientists discover this new crater? How do they know its impactor contributed to the extinction of the dinosaurs? And perhaps the most intriguing question, how many more such craters from that ancient period may still lie undiscovered? The story behind the discovery of the NAD crater is captivating. It was found entirely by accident while a geologist based in Edinburgh was working with seismic data from a seabed. Originally, he was studying data related to seafloor spreading, a geological process that gradually widens the Atlantic Ocean by slowly separating the African and American continents. While analyzing the data, the geologist anticipated seeing flat sedimentary sequences on the plateau. However, what he stumbled upon was completely unexpected, leading to the discovery of the NAD crater. The team found an 8.5-kilometer-wide depression beneath the seabed, featuring several unusual characteristics. The depression was nearly circular in shape, with a raised rim and a prominent central uplift. Additionally, there were structures suggesting chaotic sedimentary deposits extending tens of kilometers beyond the crater. Typically, craters on Earth are formed by the collapse of a volcano or by salt withdrawal processes. However, the features of the NAD crater did not match those of traditional craters. Instead, its characteristics resembled impact craters created by collisions with asteroids. After considering these findings, the team concluded that the NAD depression likely resulted from one such cosmic impact. The NAD crater is located about 350 kilometers off the coast of the African countries of Guinea and Guinea-Bissau, spanning approximately 9 kilometers in diameter. Currently, the water depth at this location is roughly 900 meters, and the crater is covered by a thick layer of marine sediment, measuring between 300 to 400 meters. The size of the NAD crater is significantly smaller than the Chicxulub crater. However, when the researchers examined its position with respect to various geological layers, they concluded that it is also around 66 million years old. While there is some uncertainty about the exact timing of the impact, the best estimate suggests that it dates back to the era of the Chicxulub impact. This implies that the two impacts may have been related. To gain detailed insights into the crater, the researchers used computer modeling and simulations. Their analysis suggested that the NAD crater could have been formed by the impact of a 400-meter-wide asteroid colliding in waters about 500 to 800 meters deep. This impact would have triggered widespread regional devastation, including a 6.5 magnitude earthquake and a colossal tsunami nearly 900 meters high that would have circled the globe. The energy released by the NAD impact is estimated to be 1,000 times greater than the tsunami caused by the underwater eruption of the Hunga Tonga Hunga Harapai volcano on January 15, 2022. The estimated size of the asteroid is comparable to asteroid Bennu. Connecting the NAD impactor to the Chicxulub impactor opens up several intriguing possibilities. Large asteroids are often accompanied by smaller moonlets, and it is possible that the NAD impactor was one such moonlet trailing the Chicxulub impactor. Furthermore, there are confirmed instances of dual impacts in Earth's history. One example is the 47-million-year-old Lni and Mingan craters in Sweden, which support the possibility of such paired impacts. Another hypothesis suggests that a massive parent asteroid or comet may have broken into several smaller fragments during a close encounter with Earth, resulting in multiple impactors of the same age. This would be similar to an event in 1994, when Jupiter's tidal forces tore apart comet Shoemaker-Levy 9, causing its fragments to collide with the planet's atmosphere. Additionally, scientists speculate about the occurrence of an impact cluster, a period characterized by frequent meteorite impacts resulting from the collisional breakup of a main belt asteroid. If this theory is correct, we might even place the Bolsh crater, estimated to be 65.4 million years old, in the same impact group as the Chicxulub and NAD craters. However, these theories are still uncertain. There is a slight chance that the NAD crater might be a collapsed volcanic structure unrelated to the Chicxulub impact. Throughout Earth's history, high-velocity impacts have left their mark. Impact events with risky impactors, those around 50 meters in diameter, occur approximately every 900 years, while larger impactors, over 1 kilometer wide, which pose a global catastrophic risk, collide with Earth about once every million years. Despite these occurrences, precise information on such impactors remains limited. With over 70% of Earth's surface covered by water, it is likely that most impact craters on Earth have marine origins. However, only 15 to 20 confirmed high-velocity impact craters have been identified as marine events. If scientists confirm the cosmic origin of the NAD crater, it would become one of fewer than 20 known marine impact craters on Earth. This discovery would challenge our understanding of the extinction event that ended the reign of the dinosaurs, prompting us to reconsider what else might have happened. Did the Chicxulub impactor have more companions? If so, where might their signatures be found? Could we discover more craters like NAD in the future? The questions are endless, and we hope that future research will bring us closer to the answers. This marks the 25th episode of the Sunday Discovery series. If you enjoyed this video, please like it, subscribe to our channel, and press the bell icon to stay updated on future episodes in this series. The original goal was to study seafloor spreading, a geological phenomenon responsible for gradually widening the Atlantic Ocean as the African and American continents drifted apart over millions of years. While analyzing the seismic data, the geologist anticipated seeing flat sedimentary layers lying undisturbed on the plateau. However, what he discovered was completely unexpected, and it opened up an entirely new chapter in the understanding of Earth's history. Instead of flat layers, the team found a striking 8.5 kilometer wide depression beneath the seabed with characteristics that immediately stood out. This depression was almost perfectly circular, featuring a raised rim and a prominent central uplift, both hallmarks that hinted at an impact event. Furthermore, there were structures extending tens of kilometers from the crater, indicating chaotic sedimentary deposits that could only have been created by an intense, high-energy collision. While craters on Earth can form from volcanic collapses or processes involving salt withdrawal, the unique structure of the NAD crater strongly suggested an origin quite different from the usual geological suspects. The researchers concluded that this depression was likely formed by a cosmic impact, the result of a space object colliding with Earth and leaving its mark deep under the sea. The NAD crater lies around 350 kilometers off the coast of Guinea and Guinea-Bissau in West Africa, a significant distance from any major landmass. At approximately 9 kilometers in diameter, it is considerably smaller than the Chicxulub crater. Today, it rests beneath 900 meters of ocean water, covered by an additional layer of marine sediment roughly 300 to 400 meters thick. Although the NAD crater's size is dwarfed by the Chicxulub crater, its age and positioning within specific geological layers intrigued scientists. By examining sediment deposits, they determined that the NAD crater is approximately 66 million years old, placing it within the same time frame as the Chicxulub impact. This tantalizing connection suggests that the two impacts might indeed be related, offering the first hint of a potentially larger extinction story that is just beginning to unfold. To delve deeper into this relationship, researchers employed advanced computer modeling and simulations. These models revealed that the NAD crater could have been formed by a smaller asteroid, roughly 400 meters wide, impacting water depths between 500 and 800 meters. Such an impact would have resulted in an extraordinary regional catastrophe, causing a 6.5 magnitude earthquake and generating a tsunami nearly 900 meters high that would have swept across the globe. The energy unleashed from this impact was calculated to be around 1,000 times greater than the tsunami caused by the eruption of the Tonga Harapai volcano in January 2022. This colossal release of energy places the NAD impact roughly on par with asteroid Bennu. The discovery of the NAD crater also opens up the possibility that the Chicxulub impactor had companions in our solar system. Large asteroids are often accompanied by smaller moonlets, and it is possible that the NAD impactor was one such moonlet, trailing the Chicxulub impactor and impacting Earth shortly after its larger companion. Dual impacts aren't unheard of in Earth's history. Another example is the dual craters in Sweden, the Lni and Mingen craters, which date back 470 million years and are believed to be the result of a similar paired impact. There is also a second theory that the parent asteroid or comet, which ultimately became the Chicxulub and NAD impactors, could have broken apart during a close encounter with Earth, resulting in multiple fragments hitting the planet around the same time. This scenario is reminiscent of the 1994 event, when Jupiter's